Hello again, everyone, and welcome to another video lecture for Psych 370. This is your fourth and final video lecture for week 5 of the course. And in this one, I'm going to cover one more important theory of classical conditioning with you, which is called the Rescorla-Wagner model. Now, guys, this theory is actually a little different from the other theories of classical conditioning that we've covered so far, because the Rescorla-Wagner model doesn't so much try to explain why classical conditioning occurs as it tries to predict when it will occur. So what the model tries to do is predict what's going to happen during each acquisition trial when the CS and the US are being paired together, and also what's going to happen during each extinction trial when the CS is presented alone without the US. Now, there is a little math involved in this one, but it's not super complicated, and I'll walk you through it. And guys, conceptually, if there's one word that I hope comes to mind for you after you've learned about the Rescorla-Wagner model, then that word would be surprise. So the Rescorla-Wagner model is basically an explanation. It's a mathematical explanation of what happens during each trial of a classical conditioning procedure. And it suggests that the amount of learning that occurs on each trial depends mainly on how surprising the occurrence or the non-occurrence of the unconditioned stimulus is. So how surprising is that event to the animal? For example, if the unconditioned stimulus is very surprising to the animal, if the unconditioned stimulus occurs when the animal doesn't expect it at all, then a lot of learning will take place. Then we'll see a large increase in the strength of the conditioned response. However, if the occurrence of the unconditioned stimulus does not surprise the animal, if the animal completely expected that US to occur when it did, then no learning will take place. The animal won't change at all how it responds to the conditioned stimulus. So, in other words, its conditioned response will stay the same. So that's the most basic thing to remember about the Rescorla-Wagner model. When you think about the Rescorla-Wagner model, think surprise. How surprising, how unexpected is the US? That is the key factor in this theory. Now, that basic principle that the amount of learning depends on the amount of surprise that the animal experiences, that principle has been captured in a mathematical formula, which we're about to go through. So again, don't worry, it's not an overly complex formula. There are really only 4 basic components to it. So the formula itself is shown here at the top of this slide. But before we actually use that formula in an example, let me take a few minutes here to go over each component. First, we have the Greek letter lambda, which is what this symbol represents. And guys, the size of lambda depends on the strength, the actual strength of the unconditioned stimulus. So one important assumption that the Rescorla-Wagner model makes is that there's a limit to how much conditioning can occur with a particular US. All right, there's a limit to how strong the conditioned response can get. And the higher that limit is, the bigger lambda will be. So lambda is also essentially the maximum strength of the conditioned response. It's the ceiling as far as how much conditioning can occur. But the stronger the unconditioned stimulus is, the stronger that conditioned response can get. So that's why I said that the value of lambda depends on the strength, the actual strength of the US. So if you ring a bell and then you give your dog a big juicy steak, if you follow the bell with that big high strength US, the steak, then the dog's going to wind up salivating to the bell a lot more than it would have if you had rang the bell and then given the dog just a little piece of kibble, right? Because again, the stronger the US is, the stronger the CR can become. So that's lambda. It's technically the asymptote of the learning curve, okay? It's the total amount of conditioning that can possibly occur. But again, a good way to think about it is to equate it with the actual strength of the unconditioned stimulus and the maximum strength of the conditioned response. Now, one reason I tell you to think about lambda like that as the actual strength of the US is because then you can think of this next component, V, as the expected strength of the US. So, V, The V stands for value. And technically, what we're looking at here is associative value or predictive value. So how strongly does the animal associate the CS with the US? What's the associative strength there? Or how good of a predictor of the US does the animal think the CS is? In other words, after the animal detects the conditioned stimulus, what does it expect to happen next? Does it expect the unconditioned stimulus to occur? And if so, how strong of an unconditioned stimulus does it expect? V represents the answer to those questions. And obviously, as we present more and more pairings of the CS with the US, that value, V, is going to increase because the animal is going to start to associate those stimuli more and more strongly. It's going to learn to expect the US after it detects the CS. So technically, V is defined as the strength of the association between the CS and the US. But again, another good way to think about it is that it's the current strength of the conditioned response. Lambda is the maximum strength, right? Lambda represents the greatest possible strength that the conditioned response could ever reach. And V is the current strength of that conditioned response. But again, that value is going to change with each trial as the animal learns, as it develops more and more accurate expectations about the strength of the US. Okay, so lambda is basically the maximum strength of the conditioned response. And again, lambda depends on how strong the US that you're using is. V represents the current strength of the conditioned response. And we can also think of that as the expected strength of the US. Next, we have the lowercase letter c, which is a constant that represents the rate at which conditioning is going to proceed. So in other words, C represents how quickly the animal is going to learn to associate the conditioned stimulus with the unconditioned stimulus. So that's what C represents. It's the rate of conditioning. And the exact value of C is going to depend on the particular stimuli that we're using as the CS in the US. So for example, C will be greater if the animal is biologically predisposed to associate those stimuli, like it would be if the CS was a taste and the US was some kind of nausea-inducing drug. And if the unconditioned stimulus is especially intense, then not only will lambda be greater, but C will as well. So in other words, with a bigger, stronger, more intense US, the maximum strength of the conditioned response will have a higher ceiling because lambda will be greater, and the actual conditioned response will approach that ceiling more quickly too, because C, the rate of conditioning, will also be greater. Now, I should probably point out here that this formula that we're looking at is a slightly simplified one, okay? Because Rescorla and Wagner actually broke this part of it, C, down into multiple subcomponents, one representing the CS and one representing the US. For our purposes, though, you don't really need to worry about those subcomponents. The main things to remember here are just that C is a constant, it represents the rate of conditioning, and the exact value that it takes depends on the specific stimuli that are being paired. So, lambda, V, C, and finally I saved the simplest component for last because the letter N just represents the trial number. So is this the first pairing of the CS in the US? Is it the second pairing? Is it the 27th pairing? That's what N tells us. So remember that what this formula is designed to do is to predict the amount of conditioning that occurs on each trial. It tries to predict how much of a change in the conditioned response we're going to see after each acquisition trial, where the CS and the US are paired, and also after each extinction trial, where the CS appears alone without the US. That's what we're calculating when we use this formula, which we're about to do. So guys, this triangle here is the Greek letter delta, okay? And delta means change in. So every time we use this formula, we're calculating the change in V. We're calculating the change in the conditioned response that occurs as a result of a particular trial. So this part of the formula that's in parentheses here is a very important piece of it because this quantity, this lambda minus v quantity, that represents how surprised the animal is by the occurrence or the non-occurrence of the unconditioned stimulus. So by definition, something is surprising to you if it's different from what you expected, right? That's what surprise is. It's a violation of an expectation. So what this value, Vn minus 1, represents is how strong of an unconditioned stimulus the animal has come to expect as of the most recent trial, the trial that occurred before the one that we're on now. So the current trial is trial number n, right? So the trial before this one, the most recent trial, is trial number n minus 1. And again, that's how strong of a US the animal has come to expect up to this point, up to this trial. And the more that value differs from this one, the more that expected US differs from the actual US, which is represented by lambda, then the more surprised that animal was by the actual US. And like I said before, surprise is the key factor in the Rescorla Wagner model. The more surprising the unconditioned stimulus is, the more the animal learns. But less learning will take place on trials where the unconditioned stimulus is less surprising. The animal won't learn as much from those trials where the expected US is more similar to the actual US, because on those trials, this quantity, this lambda minus v quantity, will be closer to 0. And so based on the formula, we won't see as big of a change in the conditioned response on those trials. Okay, well, I hope I made all that clear enough. But I think a concrete example will help here too. So let's start plugging some actual numbers into this formula and see how it works. First, let's let C equal 0.2. So we'll say that given the nature of the stimuli that we've decided to use as our CS and our US, C is going to take on a value of 0.2. Remember, C represents the rate of conditioning, and it's a constant. It doesn't change. So on every trial, every time we use this formula, C is going to equal 0.2. Again, lambda represents the maximum strength of the conditioned response, and that value depends on the strength of the unconditioned stimulus that we're using. So for the sake of simplicity, let's let lambda equal 100. So in other words, we're using an unconditioned stimulus that will support a maximum CR strength of 100, however we want to operationalize that. So if we're using a tone as the CS and food as the US, then maybe that food elicits 100 drops of saliva. So the strongest possible conditioned response, the strongest possible response to the tone would be 100 drops of saliva. That's the ceiling. That represents how much conditioning can possibly occur. So that value, 100, is the maximum strength that the conditioned response can reach. So we have our value of C, we have our value of lambda, and finally, before we start the pairings, there isn't going to be a conditioned response, right? So before that first acquisition trial, V is going to equal 0. To keep going with the Pavlov example, if we're going to be using a tone as our CS, then that tone is going to start this process as a neutral stimulus, right? It won't elicit any salivation at all. In other words, at first, the animal has absolutely zero expectation that the food is going to occur after the tone does. And that means, of course, that on that first acquisition trial, the food is going to be very surprising to the animal, right? Because after all, it expects no US. The expected value of the US is 0, but it actually gets a US with a strength of 100. So if we plug those numbers into our formula and do the calculations, we get a value of 20, right? Because obviously 100 minus 0 is 100, and then 100 times 0.2 is 20. So As a result of the learning that occurs on this first trial, this first pairing, the conditioned response increases by a value of 20. Delta V equals 20, that's what we calculated, and that was the first trial, so V itself has increased from 0 to 20. So now, going into trial number 2, the conditioned response has a current strength of 20, right? V is now equal to 20 prior to the second trial. So when we actually run that second trial, when we actually present that second pairing of the tone and the food, then the food is still going to be surprising to the animal, but not as surprising. The food is going to be less surprising to the animal on this trial than it was on the first trial, because now, as a result of that first trial, the animal has started to develop some expectation of the food, right? It's starting to form that association between the CS, the tone, and the US, the food. So when we apply the formula this time, we get a smaller change in the strength of the conditioned response. It was 20 after the first trial, and you can check my math here if you want, but I think you'll find that it increases, it changes by only 16 as a result of the second trial. So after 2 trials, the conditioned response has a strength of 36. 2 pairings in, V has increased from 0 to 20, and then from 20 to 36. So of course, we'll plug that value, 36, into our formula for the third trial, and we'll again find that while the conditioned response is still increasing, it's increasing by a smaller amount. So the food is becoming less and less surprising to the animal. The food is becoming more and more expected by the animal, and so it's learning less on each acquisition trial than it did on the acquisition trial before it. And of course, if we continue this process, then we'll get that classic pattern that acquisition curves tend to have, where the biggest gains, the biggest increases in the conditioned response happen on the earliest trials, and then they're followed by progressively smaller increases. So the Rescorla-Wagner model predicts correctly the shape of the acquisition curve. It also predicts the shape of the extinction curve. So for example, let's say that we've presented our animal with enough tone plus food pairings that now it fully expects to receive the food after it hears the tone. So the conditioned response to the tone is now as strong as it can get, in other words. So V equals 100, more or less. The conditioned response is at that maximum level of strength that it can reach. And now we're going to put that animal through some extinction trials where we present the tone, but we don't present the food. So we present the CS, but not the US, right? That's how extinction works. Now, on that first extinction trial, the animal fully expects the food, right? Again, V equals 100, but no food actually occurs. This is extinction, so there is no unconditioned stimulus. So lambda, the actual strength of the unconditioned stimulus, is now 0. V equals 100, but lambda equals 0 because there is no US. So once again, our animal is going to be surprised, right? The expected value of the US was, again, very different from the actual value of the US, so we should see a change in the strength of the conditioned response. And of course, we do see that change, but this time it goes the other way. Delta V is a negative value now, so the strength of the conditioned response decreases. It was at 100 before this first extinction trial, but now, as a result of that trial, it's only 80. Then, on the second extinction trial, the absence of the food again surprises the animal, but not as much. So this time, there's still a difference between the expected US and the actual US, but there isn't as much of a difference. So the absence of the US is less surprising now, so the conditioned response decreases by a smaller amount. And of course, this process would continue throughout all of the extinction trials, and it would produce that typical pattern that we see in extinction curves, with big decreases in the CR occurring early, followed by progressively smaller ones. So, one nice thing about the Rescorla Wagner model is that it gives us a way to account for the pattern that classical conditioning tends to follow. The shapes of the acquisition and extinction curves are consistent with what the model predicts. Another strength of the Rescorla Wagner model is that it can also explain why the blocking effect occurs. So, just to refresh your memory of the blocking effect. Remember, last week I told you guys about an experiment that involved pairing a light and a tone together with shock, right? So we present this light and tone together as what we call a compound stimulus, and then we follow that compound stimulus with shock. Well, if you recall, in that experiment, the control group only experienced pairings of the compound stimulus, the light and the tone, with shock. And those rats did acquire conditioned responses to both the light and the tone. They froze when they saw the light all by itself, and they also froze when they heard the tone all by itself. Again, that's the control group. However, for the rats in the experimental group, before they got any of those pairings involving the compound stimulus, they first got pairings where the tone, and only the tone, was paired with shock. Then, after that, they went through the same procedure that the control group did, where they got pairings of the light plus tone compound with the shock. And the results were that those rats did acquire a conditioned response to the tone, but they didn't acquire a conditioned response to the light. So, for those rats, the ones in the experimental group, their previous association of the tone with shock blocked an association from forming between the light and the shock. And that's called the blocking effect. Again, we covered that last week. Well, according to the Rescorla Wagner model, that happened because when the shock occurred after the light, it didn't surprise these rats in the experimental group. Since the light had only ever occurred alongside the tone, and since the animals already expected the shock after they heard the tone, they didn't learn that the light also signaled that a shock was on the way. So let's try to visualize how the Rescorla-Wagner model accounts for the blocking effect by looking at this graph, which is going to represent a situation where lambda equals 100, c equals zero point 0.5, and the animals get one pairing of tone and shock before they start getting pairings of a tone plus light compound and shock. So, as you can see here, as a result of that first pairing between just the tone and the shock, V increases from 0 to 50. So it gets halfway to lambda, halfway to the maximum strength that that conditioned response can reach. So that first trial has the effect of making the shock, making the US, a more expected event for the animal. So the animal is learning to expect the shock after it hears the tone. Then, on trial number 2, we introduce the light. So now, on the second trial, we're presenting the tone and the light together as a compound stimulus, and then we're following that compound stimulus with shock. However, this time, the shock is not as surprising for the animal, right? There isn't as big of a difference on this trial between the actual US and the expected US, so there's less learning on this trial. This trial doesn't produce as much of an increase in the conditioned response, and the increase that it does produce, the change in V that it does produce, gets divided up between the tone and the light. And so the result is very little conditioning to the light, very little acquisition of a conditioned response to the light. And of course, in this example, we're talking about a situation where the tone was only paired with the shock one time before we added in the light. But what I hope you see here is that even more blocking of a conditioned response to the light would have occurred if we had waited longer to introduce the light. So, for example, if we had done 3 tone and shock pairings before we ever paired the tone and light compound with shock, then the results would look more like this, where the animal acquires almost no conditioned response at all to the light. Okay? So again, the Rescorla-Wagner model can explain why the acquisition and extinction curves look the way they typically do, and it also gives us a way to understand why the blocking effect happens. And guys, the ability of this model to account for those and other classical conditioning phenomena have made the Rescorla-Wagner model very popular. That's why we're covering it in the course. However, like the other theories that we've covered, it isn't without its limitations either. For one thing, it explains extinction as being essentially the reverse of acquisition, and as we saw last week, that isn't necessarily the case. So, the Rescorla Wagner model has a hard time explaining phenomena like spontaneous recovery and rapid reacquisition. And another problem for it is latent inhibition, that CS pre exposure effect that I talked about last week. So remember, the basic phenomenon there is that if you repeatedly present a neutral stimulus, like a metronome, all by itself, and then you later pair that stimulus with a US, like food, then the animal will not acquire a conditioned response. It won't learn to salivate in response to the metronome. Or at least it'll take more pairings for it to learn that than usual. You'll have to pair the metronome with the food for longer than you normally would before the animal will start salivating when it hears the metronome. So, either way, we'd say that this animal's pre exposure to the metronome has inhibited its ability to associate that metronome with food. So, again, that's called latent inhibition, or we also call it the CS pre exposure effect. Well, the Rescorla Wagner model does not predict that phenomenon. It doesn't really have a way to explain why this would occur. After all, when the metronome first appears all by itself during this pre exposure phase, the dog has no expectation that food will occur, so V equals 0. And of course, no food does occur, so lambda equals 0 as well. So the animal is not surprised because lambda minus v equals 0. What actually happened is exactly what it expected would happen. And that means that no learning should be occurring during that pre exposure phase, right? So v, the expected value of the US, should remain at 0. And when we finally start the metronome and food pairings, the food should be very surprising to the animal. And so we should see V increasing as it normally would. We should see the animal go through the normal process of acquiring a conditioned response to the metronome. But of course, that's not what happens. Again, what actually happens is that acquisition is inhibited. It's slower than it normally would be due to that initial pre exposure phase. So, in terms of the Rescorla Wagner model, when we first start those metronome and food pairings, it looks like there's a negative value of V that the animal has to sort of overcome before it can start expecting the food, before it can start turning V into a positive value. But the model can't really explain why that negative V value would be there in the first place. Because again, the lack of food during the pre exposure phase would not have been surprising to the animal. So there's no real reason, based on the logic of this model, why that pre exposure phase would have caused V to change from its initial value of 0. So again, we return to that theme of no one theory being able to account for all of the phenomena that researchers have discovered regarding classical conditioning. Now, other theories can explain why latent inhibition occurs, but we won't get into those. And besides, they have their own limitations as well. But in any event, I hope that you now have a better understanding of psychology's current understanding of classical conditioning. None of these theories that we've covered is perfect, but they are among the strongest and most widely accepted theories that psychologists have been able to come up with, and so they represent our best efforts to explain this seemingly simple but deceptively complex type of learning, classical conditioning. Okay, well, that's going to do it for this week's video lectures. Please do reach out and let me know if you have questions about any of this stuff. And please also make sure to get your tasks for this week done and submitted in Canvas before the week comes to a close at the end of the day on Sunday. Take care, guys.